keep going forward. So, all right, so I'm going to talk about this ASTERIA mission, kind of as a case study for the mission design process that I know that you're working through right now. So let's start with kind of a scaffolding for how this usually works. Step one for designing a mission is you have to have an idea. Sometimes you have an idea that relates to a gap in our knowledge of science in whatever field. Sometimes it's a technology gap, something that you want to try out in space that might enable science in the future. And excuse me, sometimes it's expansion or continuation of something that's been done before. So you've flown something in space and now you want to fly a slightly better version. That's also fairly common. And then usually you write a proposal. So you figure out how to link your science or technology to mission specifications, the size of the spacecraft, the power, the communications and things like that. Typically you use a tool called a science traceability matrix to do that, or sometimes a technology traceability matrix, which links the high-level science goals to more specific questions to specific requirements for the mission. And then, of course, you have to figure out how much it will cost and how long it will take and who will do the work. So that's the budget, the schedule, and what we call a work breakdown structure in NASA language. And then, you write a bunch of pretty words and make pictures that kind of wrap everything above. And finally, if you're very lucky, you get to build and fly a mission. So you do a preliminary design and then that gets reviewed. And then you do a final design. Then you build it. Put it together, do your testing, usually with another review in there. Launch the thing and start operations. And hopefully if everything has gone well up to this point, then you get to do some science. So that's the general process. ASTERIA went through this general process with a few kind of special caveats that I'll talk about. So let's talk about the ASTERIA mission, which was my first CubeSat mission. It holds a special place in my heart because it was the first time I got to go through this full cycle from concept to design to execution and science data. So to set the scene here, when I was born, there were no confirmed exoplanets. We thought probably there were planets around other stars, but we had not come up with the evidence for that yet. At the turn of the millennium, there were about 7. And as of last night, when I was putting this presentation together, there are 6,042 confirmed exoplanets in the NASA Exoplanet Archive. So the point of this is that the field of exoplanets has had really explosive growth over my academic career, really. And so there has been tremendous interest and a lot of investment in finding exoplanets and now characterizing them. And we found some really cool ones. These exoplanet travel posters are some of my favorite things that have come out of the field. So this one is for Kepler 16b, which is a circumbinary planet. And so it's a place where your shadow always has company. So how do we find these exoplanets? There are a number of methods. I'm going to focus on the one that's relevant to ASTERIA, and that is the transit method. So a transit is when the planet crosses the disk of the star from our perspective on Earth. And so the planet blocks a portion of the light from the star. And if you can measure that light very, very precisely over time, you'll actually see a dip in the brightness, which represents the amount of light that the planet has blocked. And so if you can make this measurement, which is challenging, then you can measure the radius of the planet, which is a really important parameter. And then if you happen to be doing this for a star that is bright, that's very important. The star has to be very bright. You have to have a lot of photons coming to you. You can actually start looking at what's in the atmosphere of the planet. And this is because when the planet is transiting, it's crossing the star, light from the star is going through the atmosphere. The solid body of the planet blocks light entirely, but some light filters through the atmosphere. And as it does that, you get a spectrum imprinted. The planet's atmosphere spectrum is imprinted in that starlight. So then if the planet goes back behind the star, then you have the starlight only, and you can subtract those two things and extract the spectral signature of the planet's atmosphere. And this is what the James Webb Space Telescope is doing for many exoplanets right now, although I think they generally do emission spectroscopy, but the concept is the same. You're getting the spectral signature of the gases in the atmosphere of the planet, which is how eventually we will search for signs of life. So being able to do transit spectroscopy is really key to understanding a particular planet in detail and searching for signs of life eventually. So planets that transit are special for this reason. So one of the sort of long-standing goals, I would say even before we actually had exoplanets detected, was to find a planet out there in the universe that's like our Earth. And if we can learn about what it's like, maybe we can understand a little bit how our Earth came to be the way that it is. So when I say Earth-like or Earth 2.0, that has a fairly specific meaning. It means it's Earth-sized in terms of radius and mass. It is in the habitable zone of its star, which is the range of distance from the star where the equilibrium temperature indicates that liquid water could be present. And it needs to be orbiting a bright, nearby, sun-like star. So the spectral characteristics of the star should be similar to the sun, because there are lots of planets around stars not like the sun, but they're very different environments than our sun. And so if we're looking for an Earth twin, you really want a sun-like star, because that's the most similar to conditions on Earth that we can get. So there have been a number of surveys that have really pushed up that planet count to the very high level that you saw, over 6,000 confirmed exoplanets. The first one of those, the Kepler telescope, tended to focus on dim stars, mostly to get statistics, to get a large number of stars. It looked at a patch of sky with many, many, many stars that were fairly dim so that it could kind of get the statistics of exoplanet occurrence. So that's not very helpful for transit spectroscopy. You can't really do much for those dim stars. A more recent survey, the TESS mission, has looked generally at short period planets with fairly short orbits around their stars. So again, that's not really Earth-like, but we have learned a tremendous amount from that survey nonetheless. So there's kind of a challenging gap where you need a telescope kind of dedicated to bright stars in order to find transiting planets around these bright sun-like stars that you can then do spectroscopy on. So one concept that we worked with that led to ASTERIA was, well, what if you just put one small space telescope in space for each, n nearby bright stars? Then you could just watch them for a year or two and see if there are any transits, and any transiting planets you found would be incredibly valuable. But big existing space telescopes can't really do this. You can't ask the Hubble Space Telescope to stare at Alpha Centauri for 2 years because other people need to use it. So the only really reasonable way to do this is to have dedicated, cheap telescopes to look at each star, or the Plato mission, but that came later. So this is what we wanted to do way back when I was still an undergraduate in 2005, 2006, 2007. And what we decided is that we needed to demonstrate some key technology before we could go forward with this plan. So here's the science gap. I mentioned earlier that, usually an idea for a mission comes out of a science gap or a technology gap. This is the science gap. We don't have the right observatories to look for these really precious, Earth 2.0 Earth twins. So it turns out that this was around the same time CubeSats were becoming a common thing in the space world. They were really coming to prominence in that same time period. And it was a bit of a struggle to get the astrophysics community to embrace CubeSats, because in astrophysics, typically you just want the next telescope to be bigger and better than the one before. More aperture is usually the way that things go in astrophysics. But when you want to do long duration observations of a single target or a small number of targets, those big telescopes that are very expensive and have many users, many use cases, they're not well suited. It's not the right tool for the job. So CubeSats offer the opportunity to do valuable astrophysics measurements on bright targets, since they're small, the apertures are small, in a complementary way to the bigger surveys and the bigger telescopes. And I'll note here, as we've been talking a little bit about GOLO, that another niche for CubeSats is in situ multi-point measurements or constellations capable of interferometry. So you have to find the right task for a CubeSat. It's never going to replace a Hubble, but that's okay. There's things that Hubble can't do that CubeSats can. So let's talk a little bit about what this data looks like that we want to collect with our CubeSat telescope. So here's some data from the Kepler Space Telescope. This is the one that looked at fairly dim stars, but many of them. And look at this beautiful light curve. That's what we call it when we measure the brightness as a function of time. So, you have brightness here, and look at how small these numbers are, right? There's a very small change in brightness. And where the red triangles are, there's very clear transits. The brightness drops, and it does so in a periodic fashion, so you can measure the orbital period of the planet as well as its radius. But the data does not show up looking this nice. This is what it looks like when it comes from the telescope. When you downlink it via your communication system, it looks like this. So that if you already know where the transits are, maybe you can pick them out, but how would you know this is a transit and this is not, right? Or, this is a transit and this is not. You can't. The transits do not come out of this data until you clean it up to make it look like this. And many of these excursions and these wibble wobbles are instrumental effects. So here, this is pointing offset. This is a thermal effect. This is when the spacecraft went to safe mode. So you have to be able to correct for all those effects to turn this into this. And that's challenging. And there are some effects that are very difficult to correct for because they're difficult to measure on the spacecraft. So I'm going to talk about one of those, and that's pointing jitter. So pointing jitter means that your telescope is not pointed exactly where you want it to be, or it kind of moves around that pointing that you've assigned it just because no control system is perfect, right? And there's also disturbance effects in space. So here's a pixel. This is a pixel on an array detector, and every pixel has slightly different sensitivity than the pixel next to it. And even worse than that, you've got different sensitivity within the pixel. Okay, so these contours you can think of them as sensitivity. And imagine you've got a star spot that you've really pinned down to the center of your pixel where the sensitivity is maximized. So you make a measurement of the brightness of the star. But then your pointing changes. Your pointing jitters a little bit. Maybe the spacecraft is disturbed in some way, and then your star spot moves to another part of the pixel where the sensitivity is a little less. And so, your curve decreases. Maybe it moves even farther and your curve decreases more. And now it's come back to the center and your signal's gone up again. That kind of looks like a transit, but it is not. It's an entirely instrumental effect. And it's one that's very hard to take out after you've collected the data. So to the extent possible, you want to minimize this pointing jitter so that you don't have to worry about this factor. It's so small that it doesn't matter relative to the signal you're trying to detect. So this was, for us, the technology gap. How do you point a CubeSat, a very small, low-mass spacecraft, well enough that your signals are not swamped by pointing jitter? So that was what inspired what we originally called ExoplanetSat. And the original goal of this student design mission was to observe one star, Alpha Centauri, for 1 to 2 years to see if there were any transiting planets around our closest sun-like neighbor. Just to be clear, Alpha Centauri is a binary system with 2 sun-like stars. Proxima Centauri is an M dwarf that orbits that binary. So it's a triple system, two-level triple system. alpha Cen, A and B are the sunlight components, and they're our closest neighboring sun-like stars. So this was a class that I was part of. I'm in here. And over 3 semesters, we designed a spacecraft to address this challenge. And so the pointing system was a major part of it. We built a little model, which I think is still in the department somewhere. This was the CAD model for the spacecraft that we designed. There was a deployable baffle for the telescope. The telescope was here with all the electronics and deployable solar panels. So this was a student project, and we came up with a design that we thought could address the science and technology gap that I just described. So then what happened? Well, one thing that we did as part of that process is we designed a pointing system that could address the pointing jitter problem. So you've got a lens here. This is a refractive optical design. So lenses, glass lenses. And then behind the lens, you have to have your detector. So that's here. That's what we call the focal plane. And generally, you're controlling the pointing with reaction wheels, which can have some jitter and some errors. And the design that we came up with, Chris Pong primarily, was to put that detector, that focal plane, on a piezoelectric translation stage. So if your pointing shifts, we are monitoring the position of stars on the focal plane, and we can use the piezoelectric stage to move the focal plane itself to put the stars back where they're supposed to be. So it's like a Steadicam, basically. It's a Steadicam for space that very precisely keeps stars where you put them on your detector so that you don't have to worry about the effect of that pointing jitter error. We also looked at thermal control. Some of this came a little bit later than the class, but the basic problem is this. You've got, temperature in orbit fluctuating as you go from sunlight to shadow and sunlight to shadow. And any temperature variation can also change the effective sensitivity of your detector, and you don't want that. So with really good isolation of the payload and the detector from the rest of the spacecraft, so that's just making sure heat can't transfer, we can get our variation across an orbit down to a couple degrees C. But that is not sufficient. That's not good enough for the science that we want to do. So the design that we came up with was passive cooling, so letting as much heat as possible radiate out into space, but then active heating to pin the temperature just above the variability that you see orbit to orbit. So we used a heater to set that temperature. And the stability goal was 0.01 C, or 10 millikelvin, which is a pretty good thermal control for a small spacecraft. That's a challenge. And so this was one of our key technologies that we wanted to demonstrate. So we designed this mission as a student project over 3 semesters with collaboration with Draper Lab, which is in Cambridge also. It was called Exoplanet Sat, very literal name. It's a satellite to look at exoplanets. So that was from about 2008, even a little earlier through 2013. And we were looking for a home for it, to actually get to flight. And we were very lucky that JPL, the Jet Propulsion Lab in Pasadena, California, was willing to partner science too. As I said, exoplanets were really, the hot thing at the time and still are to some extent. So JPL was able to find internal funding through a program that they used to train their recently hired engineers. It was basically a training program to get people ready to work on the big missions, because you don't necessarily come out of college ready to work on, Europa Clipper or the Mars landers. So you need something to cut your teeth on. And so that was what this program was for, and it was able to fund the development of what became ASTERIA. So ASTERIA is a figure from Greek mythology. She's associated with stars and divination. I argued that we should just name the telescope ASTERIA, but I lost that argument and it became an acronym. So ASTERIA is the Arc-Second Space Telescope enabling research in astrophysics, because somehow everything must be an acronym. So here are some key parameters for ASTERIA. So it's a 6U CubeSat. So we doubled the size from the original 3U. It's 3-axis stabilized, so that means reaction wheels, a set of 3 reaction wheels, no spare. It has deployable solar panels, refractive optical telescope, so that's basically a very fancy DSLR lens. A CMOS detector, CMOS as opposed to CCD, it's a slightly different technology that is a little bit more radiation tolerant. It can read out very fast, and that was really important for us for the control system, the fast readout. It was eventually put into an ISS-like orbit. It was deployed from the space station, so that's about 400 kilometers with an inclination of 51.6 degrees. We used S-band, so two-ish gigahertz communications with a 21-meter communications dish in Kentucky. That was our communications system. It was a 3-month nominal mission lifetime. So the design was intended to be good for 3 months. The lifetime that you choose for your satellite has a lot of implications for how robust the parts need to be, for example, to radiation or thermal variability. So we chose 3 months to kind of keep the cost down. And as I mentioned, this was funded through JPL's Phaeton program for training early career engineers. So what were our goals? ASTERIA, in the transition from MIT to JPL, became a technology demonstration mission as opposed to purely a science mission. We still wanted to be able to attempt some science, but the primary driving goals were technology demonstration to enable photometric studies of astrophysical phenomena. So the first goal was to demonstrate this high precision optical line of sight pointing, so reducing that pointing jitter. And our goal was to do better than 5 arcseconds RMS pointing. So that's, it was a fairly challenging goal at the time for CubeSat systems as they existed then. We also had the goal to demonstrate high precision focal plane temperature control. So that's 10 millikelvin, no more than 10 millikelvin variability over an observation. And we also wanted to make sure that it was capable of conducting photometric measurements of astrophysical sources on an opportunistic basis, because the technology demonstration was the really driving goal and the science was sort of a, secondary thing if we had time. So here's the design. Obviously, this is a lot more detailed than the 3U CubeSat CAD model I showed earlier that we designed as students. The camera is here, the lens is here. So there's a little baffle, no more deployable baffle, just an internal one. You can kind of see the lens peeking out. So there's lenses in this housing. This is the piezoelectric stage that does that fine pointing control. So the detector's back here. This is the electronic stack that runs the detector as well as the piezoelectric stage. This is a reaction wheel and star tracker assembly. So the reaction wheels are in here. This is a GPS antenna. This is a star tracker to get our position in space really accurate. Here's the radio. This block is the patch antenna that we used, and this is the radio. And then back here, we've got our power system, basically, the electronics, as well as the flight computer. So this is what our solar panels look like when they're deployed. This is the CubeSat design. So this is ASTERIA in our clean room at JPL. I say ours if it was mine, but it was not. And this is part of the team that built and designed this mission. So it's a very shiny CubeSat. You can see the lenses. That looks really cool. Plus on top here, this is the GPS antenna. This is the communications patch antenna. There's one on the bottom as well. Star tracker here, science camera here. So then we got to go to the launch. So this is me at Kennedy Space Center. ASTERIA's way out here on the launch vehicle. This launch was a Falcon 9 resupply mission to the space station. So we went up basically as cargo. I took my dad with me, which was fun. I have to say, I don't recommend going to Florida in August. It would have been nice if the launch could have been any other time. It was a little warm. but it was amazing to see it launch. If you have the opportunity, it's well worth it. So then ASTERIA launched successfully, went up to the space station and kind of sat around as cargo until November. And then November 20th was our deployment day. And it happened to be at something like 4 a.m. California time. So we dragged ourselves to JPL, to a conference room, to kind of watch the live feed from the station. And we got to see this. There's ASTERIA with its solar panels neatly folded out into the void. So this is our last, visual contact with ASTERIA. But luckily it was not our last contact. We were able to make radio contact within a day of deployment, which was really great. So this is what happened. We delivered to the launch provider, the ASTERIA launched, we deployed, and then autonomously the solar panels deploy. The spacecraft finds the sun and points the solar panels at the sun, and then is ready to start communication. So as soon as we were able to talk to it via radio, we did some commissioning and checkout activities, and then we went into our normal operation cycle. And so the way that worked is we would talk to it during the day, it would charge up its solar panels, and during the day here is orbit day, which is about 60 out of 90 minutes. When it came into the Earth's shadow or eclipse, then it would reorient from its sun-pointed attitude to point at whatever target we had assigned it for that orbit night. It would do its observations, and then when it came out of the shadow, it would repoint to the sun, and we'd have another opportunity to communicate with it. So this is what we did, for the 90-day mission, and much more, it turned out. So let's check in. How did we do with the goals that we set? So remember, the goals were the high precision pointing, 5 arcseconds RMS, the high precision temperature control, 10 millikelvin, and of course, conducting measurements of astrophysical sources. All right, so this plot shows pointing error in arcseconds on both axes. So this is the x-axis error, this is the y-axis error. The red box is our requirement, that 5 arcseconds RMS. The blue squiggles in here, that is actually how well we did even without the fine pointing control system. So that's just the reaction wheels that we purchased from Blue Canyon. And then the red dot, which I'm going to zoom in on, that's how well we did with the secondary, the second stage of pointing control, that piezo stage that moves the detector for us. So, here's 5 arcseconds, and we are well within that box. So we actually did much better than our requirement. We got to 0.5 arcseconds RMS pointing over 20 minutes. So we exceeded our requirement by a factor of 10, which is always good to do. This plot shows how we stack up against other missions at the time. Obviously, today there would be more missions on this plot, but we compared ourselves to our peers at the time. So basically, this is spacecraft mass versus pointing stability, and so more massive spacecraft can point more precisely because they have more inertia. But small things in the same mass class as ASTERIA, we outperformed them all. We were able to point much better than any other small spacecraft at the time. Of course, that has changed today. Here's a similar plot for the focal plane temperature stability. So mass, focal plane temperature stability. There's fewer spacecraft on here because not that many missions actually need to control their temperature very precisely. But again, we did better than pretty much anything at the time in our size class. So how about that science data? So in December, remember we deployed in November, late November. We got our first light image, and we all sat around waiting for it to come down and get reassembled from the data packets, and this is what we got. So actually, if you look closely, there are little stars in here. This is a raw image, a 50 millisecond integration, no correction done. All those stripy columns that look like a barcode are just kind of artifacts of how the detector works. There's different amplifiers for each column here, and we have a mask for that. We can correct for it. And when we do, we can get images that look like this. This is not actually the same image I showed you as the first light. This was something we took later. But I really like this one because it has the Pleiades in it. And if you look at 2 frames, it actually has a comet. This is the Christmas comet in 2017. So we actually were able to take a picture of a comet moving through the solar system, which was pretty cool. So generally we didn't do full frame images, although it was a real treat when we did, because you could see things like, Saturn and Vesta, along with beautiful background stars and dust and things like that. But we didn't have the bandwidth to bring down full frame images all the time. So we had to do something different. We had to take little squares, little cutouts from the full frame image, and only download those images. So we would have a number of guide stars, which help the pointing system really lock on, and then a target, the science target, which was the star that we wanted to study in detail. And so we would collect many of these little postage stamps. They would be summed up on board into a 1-minute integration, and then that is what we would downlink to do our science. So here's what we got after many months of observation. We looked at a planet called 55 Cancri E. So this is a 2 Earth radius planet transiting a sun-like star, and we stared at it for many, many, many orbits. It happens to orbit in about 18 hours, so it is very much not Earth-like in that sense, but it's convenient because that gives us many opportunities to see its transit. So this is our light curve that we made. So this is orbital phase of the planet, because we happen to know that. So this is the center where the transit happens. And this is the relative brightness of the star. So the little gray dots are the 1-minute cadence data, and then the black dots are binned 20-minute data points. And if you just look at those, it's a little easier to see. Here's the transit. Here's the transit of that planet. Now, this is not a new discovery. We knew that this planet existed and that it transited and what its properties were. This was a demonstration. We wanted to show that we could get this fairly shallow transit with our small telescope in space. It was space-based telescopes that found this transit in the first place, and it has proven rather difficult to see this transit from the ground due to atmospheric effects. It has been done, but it took a 4-meter telescope to do it. So we did this with our little, tiny aperture. We were able to find this transit. So this was a big achievement for the team. It really showed that the concept worked. We were able to get a very small transit with little ASTERIA. This is the exoplanet travel poster for 55 Cancri. It is potentially a lava planet, although there has been a lot of recent work that maybe it's not molten on the surface. The JWST has looked at it, and it's a really interesting object, but it's very, very hot. It orbits its star every 18 hours, but it is about, a little bit bigger than the Earth, and the star is very similar to the sun. All right, so ASTERIA operated in space for 745 days. Just about 2 years, which was considerably longer than the 3 months of its nominal orbital lifetime, or design lifetime rather. So we really exceeded the spec in terms of lifetime. It was a very reliable spacecraft in the end, and it just kept going. It just kept chugging. And so after we accomplished the initial goals that we set out to do, the pointing control, the thermal control, and getting an exoplanet transit, we did a bunch of additional stuff. We did additional transit searches for Alpha Cen, as originally intended by the exoplanet sat design. We also used ASTERIA as an in-space testbed for new software, including semi-autonomous decision-making in software, which is, it's a common thing on the ground, but it's actually quite rare to let your flight software make its own decisions because, usually with assets in space, they're very expensive, and you really don't want to have your autonomous software make any mistakes and break them. So since Asteria had already, done its thing, it had achieved its goals, it was considered, reasonable to test riskier software on Asteria to show that it worked in space. And the software architecture that was tested on Asteria ended up being used for the Mars helicopter, which was pretty cool. So we had a very tiny role in the Mars helicopter, which was pretty neat. So then Asteria finally re-entered the atmosphere and burned up in the spring of 2020. So that was the end of Asteria. We did actually lose contact with it a little bit before it re-entered. We lost contact in like December 2019. We're still not sure why. It was some issue with the radio, but we'll never know. But it wasn't too far away from when it would have burned up anyway. So that was sad, but it had really done a lot in its short life in space. So we're proud of Asteria. So I want to make sure to acknowledge the team that worked on this. There was a big team at JPL, fantastic team. It was, I think, the best professional experience of my career to date was working with this team at JPL. There was a smaller team of us at MIT. Sarah Seeger was the PI, and I served a role as like a project scientist, so kind of translating the science needs and desires to the engineering team. Brees Demery and Akshata Krishnamurthy were members of that science team as well. There was a whole team at Morehead State University in Kentucky that did the communication side of things, and they did a fantastic job. And, they would, be up at 2 a.m. with us to make sure that we could talk to the spacecraft when it was available. And of course, there was the team at MIT that did the design in the first place that got this all started. So every mission is a team project. Usually you'll see maybe, the PI getting interviewed and talking about a mission, but behind that person, there's a big team, and these missions don't happen without, well-integrated functional teams. So I think the thing that is most essential to making a mission work is having a functional team and being able to work in a team efficiently and effectively, and being able to work through conflicts and disagreements in a professional manner. It's an underrated skill in engineering, but nothing happens without it. So to sum up, and I think we'll have some time for discussion, what can we learn from Asteria? I have a couple things, but I'd be really interested to get your takes on what you take away from this presentation, and what you can take forward into the design work that you're doing. So the first thing I have is that, especially for small missions, you need to find your niche. Your mission doesn't have to do everything, and it's really important to kind of pare down what you want to accomplish to the essentials, to the sort of bare minimum, so that you can quickly show that you've succeeded. So you don't want to pack your mission too full of cool things that it can do. The second thing is that there's many iterations between concept and flight. So it doesn't do you much good to get too attached to any one version or technology or particular widget. You have to stay focused on the big picture goal. As you saw, Asteria started out as a 3U CubeSat with a deployable baffle. I personally designed that deployable baffle, and I really liked it, but it ended up being a complexity that we didn't really need and would be expensive and have the potential to fail. So we ditched it, and that's okay. So you have to stay focused on getting the mission to fly, rather than, maybe the small piece that you really like or that you designed, which could be hard, but these things go through many changes, and that's okay as long as those changes move you closer to flying. And the final thing I want to say is that it's really important to define mission success carefully and thoughtfully and make it easy to claim a win early in the mission. I showed you the three goals we had. They're pretty simple, right? We had a pointing goal with a specific number we wanted to hit. We had a thermal goal with a specific number we wanted to hit. And then the, observe an astrophysical target is a pretty easy goal. As soon as we pointed the camera at, that comet, we checked that one off. And that's really important because these things are expensive. And there's always someone sort of looking over your shoulder at the budget and saying, was this worth it? Are you doing the things that you said you were going to do that we paid a lot of money to make possible? And if you can say, yes, indeed, we've hit our first milestone and we're 60% of the way to our second one, and on Tuesday we're going to check off the third one, that makes it a lot easier to kind of keep the mission going, and also potentially have future missions of a similar type. So it's important to really think clearly and carefully about how you define your mission success. If you make it too hard, you increase your chances you're not going to be able to claim success, which is not ideal. So that's all I've got. I think we've got some time for discussion and questions, and I'm curious to hear what you think the takeaways are from the ASTERIA mission. So I'm going to stop sharing so I can see